Hello students, this is lesson U2A00 and this is going to be part 1 of the introduction to the quadratic equation. So in this video what I'm going to do is just talk a little bit about the history actually. I find that when I was going through high school that this piece was missing, and even when I was in college, I felt like the origins of these important equations that we work with in math class day to day, and then designers and engineers who work with these equations from day to day. I'm not sure whether or not during our education we actually know anything about where it came from. We certainly know of the great giants, okay, such as Sir Isaac Newton or Kepler, okay. However, there are so many other giants in history that we sometimes fail to recognize. So this is my attempt, okay, to introduce and to shed some light in some of the giants that are not typically discussed in high school. So I want to apologize, okay, if I am pronouncing this name incorrectly. This gentleman, okay, by the name of Al-Khwarizmi, he was actually the father of algebra. He wrote the first book on algebra, as a matter of fact. So this gentleman actually lived about back towards about 800 AD. Sorry, let me just readjust this so that I can just go through the different layers. So he actually was a Persian man who lived back in the 800 AD, and he was the father of what we now know algebra. And why is it called algebra? Actually, this is based off of the title of his book, Algebra, and based off of this book, he was able to. It's actually a book on balancing, okay, which we all know to learn and to maximize our ability to solve problems with, right? It's this whole concept of balancing equations and balancing. It's a balancing act, okay, where we are able to then very fine tune and carve a way to getting our solution. So he actually was also one of the first mathematicians to derive the use of the quadratic formula. And this whole concept of the quadratic equation, okay, it's very interesting actually, because the quadratic equation, as we all learn to use and to manipulate with, is actually well, equations such as this, okay, were actually first used to calculate, of all things, inheritances. Okay, and this was actually a big problem that a lot of people back, in his day, where he had lived, and he needed to actually compute such quantities or solve the solutions to such type of equation. You're probably wondering, well, what does that, how does that even make any sense, right? Well, suppose the inheritance, right, based on the laws of the day, okay, which was, well, suppose this, you have a family, and in your family you have 11 kids. A lot of, people have a lot of kids back then, right? For both security reasons, as well as, just trying to make sure that they are able to pass on to the next generation, okay? So again, suppose, you have 11 children, and you want each and every one of them to get a little bit of your inheritance. However, I hate to say this, but parents sometimes do play favorites, especially back in the old days, right? So there is going to be one out of the batch that is going to receive the most. Okay, so what is this? What's the rule here? So suppose that of these 11 kids, 10 of which will have equal shares, okay, of what remains after the one child, that he will receive the square quantity of whatever everyone else receives. I said that a little strangely. So let me just read what I wrote here. Suppose a wealthy landowner having 11 children, 10 of which will receive the same amount, while one will receive the square quantity of what everyone else receives. Okay, so that's the situation. Now, if that's the case, okay, and and I'm just basing it off of this equation that I wrote here. Suppose that this wealthy landowner has 39 pieces of land or something, okay? And, well, how is that going to be evenly distributed then, right? How is that going to work? Well, as it turns out, right, and this is why he was such a revolutionary, and no one thought of making the connection between a numerical problem such as this, okay, and juxtaposing it with a geometry problem, which, in high school education, that's what we attempt to do. We actually try very, very hard to bridge the two worlds together for you guys, that there is a major connection between algebra and geometry. And what is that connection here in this case, in this particular example? Well, suppose that, we have one of the 10 children here. Okay, that's what that child is going to receive. Okay, and then the other remaining 10, this is the quantity of land that they will receive. And this is the total number of land that the wealthy landowner has. Well, how are we going to figure out how much land we are going to, pass on to each one of the children? So, when presented like this, okay, that's the thing about geometry and algebra. They're very versatile. What we can do, okay, we can actually do a little bit of rearranging, right? How can we rearrange the left-hand side? I mean, the right-hand side is it's 39. Yes, we can break up the 39 into however many parts, but we can also work with the left-hand side, even though the left-hand side has a lot of unknowns in there. So what Al-Khwarizmi, right, thought of doing was rearrange the unknowns on the left-hand side in this manner. Why is this beneficial? Well, because of the way that this is arranged right now, and both of these diagrams, okay, it's almost trying to scream at you what's missing on the left-hand side. The left-hand side looks like, hey, we need to complete that square, right? Hence that technique that you guys had learned back in 9th grade, or whenever you guys had studied Algebra 1 about completing the square. So, wait, if we were to complete that square on the left-hand side, we need to then balance that out on the right-hand side. And this was the technique that he came up with, right? By completing the square, he was then able to figure out, wait a minute, so if we complete the square in this manner, we can then be able to solve for what that unknown is, because the left-hand side basically is, right, we're dealing with a square with a length of x plus 5. X plus 5 quantity squared equals to 64. So therefore, the side of the square has to equal to 8, because if we take the square root of 64, we get 8. And then finally, if we subtract 5, then what we will end up with is 3. Okay, so this technique about on completing the square is actually, it actually changed how we think about solving equations. Okay, in particular, equations that are not linear. However, we study math nowadays. Not so much in the same linear sense as our human evolution development has been, right? It took us humans hundreds and hundreds of years to get to where we are today with our understanding of math. So what we try to do, okay, is we try to bridge different things that were discovered at different times and try to make those connections for you guys. So actually, Al-Khwarizmi, Okay, when he solved a problem like this, he failed to recognize one thing, which we now know, okay, even as high schoolers, okay, or maybe perhaps even as middle schoolers, recognize that this is actually not the only solution. So actually, this can be thought of as not just 8, but -8 as well. And if that's the case, then a second possible solution would be -13. And it is this evolutionary jump that we are able to make this kind of like declaration that this number over here, even though it's negative, actually holds a ton of significance. Okay? It is what allow us to then go from something so basic, okay, as like computing basic accounting and inheritance, okay, to doing really great things, okay, mixing in science and technology, okay, with the understanding that these other numbers actually do play a role, do play a part in the computation. We are then able to erect great works of art and architecture. We are able to not just create art for aesthetics reasons, but also create them for more pragmatic reasons. And as a way to commemorate and honor all the great discoveries that these great giants have done in the past and to where we are today, right? Great monuments such as this, okay, is created. All of these are actual examples of these quadratic equations being worked with and manipulated with and us capitalizing on. So let me just speak a little bit about this. As it turns out, right, structurally, right, the quadratic equation or the parabola, right, because that's when it's graphed, right, this is the most sound design, right? You can certainly appreciate this when you get up to a really tall tower and you feel gusts of wind up at the very top, right there, right? Certainly, you feel a lot of torque, a lot of tension, okay? So in order to counter all of that, we need a really beefy base. Well, how much is considered a beefy base? Well, to be really precise, you need a lot of math and you need a lot of engineering and a lot of understanding of science to accomplish that, right? And then same thing goes for a bridge. Why is it that under the bridge we typically find these structures in place over here? Well, that's because there's a lot of tension and stress experienced by the bridge, in particular in the at the beginning of the bridge, which is why you have so much more load over here, okay? And you actually experience much less load, okay, when we get closer towards the middle, okay? So, from a physics standpoint, okay, that stress distribution, the pressure, okay, it actually forms this parabolic shape. Okay. Yeah, and just one other word about the word quadratic. Why is it called a quadratic? Quadratic, let me just change the color here. So the word quadratic, right, just it actually means square. So the quadratic equation is a square equation. So it actually means square here. So it's a square equation, and that's actually very fitting because, based on the very early days of solving such quadratic equations, we are essentially just solving these squares, okay? And what you're going to see, okay, in the upcoming video in part 2, okay, is we're going to talk about graphing quadratic equation, which I know you guys have seen in Algebra 1. However, the quadratic equation can be defined, or actually a parabola, the shape of the quadratic equation, can be defined in other ways, which you probably have not seen before, okay? Which we're going to spend a lot of time talking about as well, which is something that's new in this course that you haven't seen. There are some things, okay, that overlap between advanced algebra and Algebra 1 and geometry, but certainly more advanced views on the quadratic equation is something that's new that we're going to talk about in the next video. Okay, I'll see you then.